Introduction to regular expressions. In this video, we are going to see about Introduction to regular expressions. In theoretical computer science and formal language theory, a regular expression that is sometimes called a rational expression is a sequence of characters that define a search pattern mainly for used in pattern matching with strings or string matching, that is, find and replace like operations. A regular expression can be recursively defined as follows. Epsilon is a regular expression indicates the language containing an empty string. L of epsilon is equal to epsilon. Phi is a regular expression denoting an empty language. L of phi is equal to null. If x is a regular expression denoting the language L of x and y is a regular expression denoting the language L of y, then x plus y is a regular expression corresponding to the language L of x union L of y, where L of x plus y is equal to L of x union L of y. X into y is a regular expression corresponding to the language L of x into L of y, where L of x into y is equal to L of x into L of y. Regular expressions. Regular set 0 plus 1 0 star L is equal to 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, goes on. 0 star 1 0 star L is equal to 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 1, 0, and goes on. 0 plus epsilon into 1 plus epsilon L is equal to epsilon, 0, 1, 0, 1. A plus B the whole star. Set of strings of A's and B's of any length including the null string. So L is equal to epsilon, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, and goes on. A plus B the whole star ABB. Set of strings of A's and B's ending with the string ABB. So L is equal to ABB, AABB, BABB, AAABB, ABABB, and goes on. 1, 1 whole star. Set consisting of even numbers of ones including empty string. So L is equal to epsilon, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and goes on. A whole star, B whole star, B. Set of strings consisting of even numbers of A's followed by odd number of B's. So L is equal to B, AAB, AA, BBB, AA, BB, BBB, AA, AAB, AA, BBB, and goes on. AA plus AB plus BA plus BB whole star. String of A's and B's of even length can be obtained by concatenating any combination of the strings AA, AB, BA and BB including null. So L is equal to AA, AB, BA, BB, AAAB, AABA, and goes on. Regular languages and its definition. In this animated video, we are going to see about regular language and its definition. Three of the languages over A, B are L1, the language of strings ending in AA, L2, the language of strings containing either the substring AB or the substring BBA are L3. The language AA, AAB star B. Like L3, both L1 and L2 can be expressed by a formula involving the operations of union, concatenation, and Kleene star. L1 is A, B star AA and L2 is A, B star AB union of BBA A, B star. Definition for regular languages over an alphabet summation. If summation is an alphabet, the set R of regular languages over summation is defined as follows. The language empty set is an element of R, and for every A element of summation, the language A is in R. For any two languages L1 and L2 in R, the three languages are elements of R. L1 union of L2, L1, L2 and L1 star. Application of regular languages. In this video, we are going to see about application of regular languages. Finding common patterns in DNA and RNA structure descriptions. Modeling natural language acquisition by humans. Learning of structural descriptions from structured example documents in particular document type definitions, that is DTD, from SGML documents. Learning the structure of music pieces. Obtaining compact representations of finite languages. Classifying and retrieving documents. Generating of context-dependent correction rules for English grammatical errors. Construction of grammar and types of grammar, 0, 1, 2 and 3 automata with output. In this video, we are going to see about construction of grammar and types of grammar, 0, 1, 2 and 3 automata with output. Grammar. A grammar G can be formally written as a 4-tuple, that is NTSP, where N or Vn is a set of non-terminal symbols. T or epsilon is a set of terminal symbols. S is a start symbol, S belongs N. P is production rules for terminals and non-terminals. Construction of a grammar generating a language. We consider some languages and convert it into a grammar G which produces those languages. Example, suppose L of G is equal to AMBN or M greater than or equal to 0 and N greater than 0. We have to find out the grammar G which produces L of G. Solution. Since L of G is equal to AM, Bn or M greater than or equal to 0 and N greater than 0, the set of strings accepted can be written as L of G is equal to A, AA, AB, AAA, AAB, ABB, and goes on. Here, start symbol have to take at least one A followed by any number of B including null. To accept string, set A, AA, AB, AAA, AAB, ABB, and goes on. We have taken the productions. S produce AA, A produce AA, A produce B, B produce BB, B produce lambda. S produce AA, produce AB, produce A lambda, produce A, that is accepted. S produce AA, produce AAA, produce AAB, produce AA lambda, produce AA, that is accepted. S produce AA, produce AB, produce ABB, produce AB lambda, produce AB, that is accepted. S produce AA, produce AAA, produce AAAA, produce AAAB, produce AAA lambda, produce AAA, that is accepted. S produce AA, produce AAA, produce AAB, produce AABB, produce AAB lambda, produce AAB, that is accepted. S produce AA, produce AB, produce ABB, produce ABBB, produce ABB lambda, produce ABB, that is accepted. Chomsky classification of grammars. This hierarchy of grammars was described by Noam Chomsky. 4 types of grammars are. The following diagram shows containment of type 3, subset of type 2, subset of type 1, subset of type 0. Type 3 grammar. They generate regular languages. They must have a single non-terminal on the left-hand side and a right-hand side consisting of a single terminal or single terminal followed by a single non-terminal. The productions must be in the form x produce A or x produce AY, where x, y belongs to N, that is non-terminal, and A belongs to T, that is terminal. The rule S produce epsilon is allowed if S does not appear on the right side of any rule. Example: x produce epsilon, x produce A, x produce AY. Type 2 grammar. They generate context-free languages. The productions must be in the form A produce gamma, where A belongs to N, that is non-terminal, and gamma belongs to T union N whole star, string of terminals and non-terminals. These languages generated by these grammars are being recognized by a non-deterministic pushdown automaton. Example: S produce XA, X produce A, X produce AX, X produce ABC, X produce epsilon. Type 1 grammar. They generate context-sensitive languages. The productions must be in the form alpha A beta produce alpha gamma beta, where A belongs to N, that is non-terminal. Alpha beta gamma belongs to T union N the whole star, strings of terminals and non-terminals. The strings alpha and beta may be empty, but gamma must be non-empty. The rule S produce epsilon is allowed if S does not appear on the right side of any rule. The languages generated by these grammars are recognized by a linear bounded automaton. Example: AB produce ABBC, A produce BCA, B produce B. Type 0 grammar. They generate recursively enumerable languages. The productions have no restrictions. They generate the languages that are recognized by a Turing machine. Example: S produce ACAB, BC produce ACB, CB produce DB, AD produce DB. Moore machine and its equivalent Mealy machine conversion. In this animated video, we are going to see about Moore machine and its equivalent Mealy machine conversion. Moore machine is a FSM, that is, finite state machine, whose outputs depend on only the present state. A Moore machine can be described by a 6 tuples, that is Q, summation O, del, X, Q naught, where Q is a finite set of states. Summation is a finite set of symbols called the input alphabet. O is a finite set of symbols called the output alphabet. Del is the input transition function where del, Q into summation produce Q. X is the output transition function where X, Q into summation produce O. Q naught is the initial state from where any input is processed, that is, Q naught belongs to Q. Example: state diagram of Moore machine. Conversion of a Moore machine to its equivalent Mealy machine. Input: Moore machine. Output: Mealy machine. Algorithm. Step 1. Take a blank Mealy machine transition table format. Step 2. Copy all the Moore machine transition states into this table format. Step 3. Check the present states and their corresponding outputs in the Moore machine state table. If for a state Qi, output is M, copy it into under the output columns of Mealy machine state table. Example: let us consider the following state table of Moore machine. Now we apply a Moore machine algorithm to convert it into Mealy machine. Step 1 and 2. State table after states 1 and 2. Step 3. State table after Mealy machine. Mealy machine and its equivalent Moore machine conversion. In this animated video, we are going to see about Mealy machine and its equivalent Moore machine conversion. A Mealy machine is a FSM whose output depends on the present state as well as the present input. It can be described by a 6 tuple, that is Q summation O delta X Q naught, where Q is a finite set of states, summation is a finite set of symbols called the input alphabet, O is a finite set of symbols called the output alphabet. Delta is the input transition function where delta Q into summation produce Q. X is the output transition function where X, Q produce O. Q0 is the initial state from where any input is processed, that is, Q0 belongs to Q. Example: state diagram of a Mealy machine. Conversion of a Mealy machine to equivalent Moore machine. Input: Mealy machine. Output: Moore machine. Algorithm. Step 1. Calculate the number of different outputs for each state, that is Qi, that are available in the state table of the Mealy machine. Step 2. If all the outputs of Qi are same, copy state Qi. If it has n distinct outputs, break Qi into n states as Qin, where n is equal to 0, 1, 2 and goes on. Step 3. If the output of the initial state is 1, insert a new initial state at the beginning which gave 0 output. Example: let us consider the following Mealy machine. Here, states A and D give only 1 and 0 outputs respectively, so we retain states A and D. But states B and C produce different outputs, that is 1 and 0. Hence, we divide B into B0, B1 and C into C0, C1. Definition of finite automata. In this video, we are going to see about definition of finite automata. Formal definition of a finite automaton. An automaton can be represented by a pi tuple, that is Q summation del Q0 F, where Q is a finite set of states. Summation is a finite set of symbols called the alphabet of the automaton. Del is a transition function. Q0 is the initial state from where any input is processed, that is, Q0 belongs to Q. F is a set of final state or states of Q, that is, F subset of Q. Finite automaton can be classified into two types. Deterministic finite automaton, that is DFA. Non-deterministic finite automaton, that is NDFA or NFA. Deterministic finite automaton, that is DFA. In DFA, for each input symbol, one can determine the state to which the machine will move. Hence, it is called deterministic automaton. As it has finite number of states, the machine is called deterministic finite machine or deterministic finite automaton. Formal definition of a DFA. A DFA can be represented by a pi tuple, that is Q summation del Q0 F, where Q is a finite set of states. Summation is a finite set of symbols called the alphabet. Del is a transition function where del Q into summation produce Q. Q0 is the initial state from where any input is processed, that is, Q0 belongs to Q. F is a set of final state or states of Q, that is, F subset of Q. Example, let a deterministic finite automata be Q is equal to A, B, C. Summation is equal to 0, 1. Q naught is equal to A. F is equal to C and transition function del as shown by the following table. Graphical representation. Definition of non-determinism finite automata, that is NDFA. In this video, we are going to see about definition of non-determinism finite automata, that is NDFA. In NDFA, for a particular input symbol, the machine can move to any combination of the states in the machine, or in other words, the exact state to which the machine moves cannot be determined. Hence, it is called non-deterministic automata. As it has a finite number of states, the machine is called non-deterministic finite machine or non-deterministic finite automata. Formal definition of a NDFA. A NDFA can be represented by a phi tuple, that is Q summation del Q naught F, where Q is a finite set of states. Summation is a finite set of symbols called the alphabets. Del is the transition function where del Q into summation union epsilon produce 2 to the power Q. Q naught is the initial state from where any input is processed, that is Q naught belongs to Q. F is a set of final state or states of Q, that is F subset of Q. Graphical representation of a NDFA, same as DFA. A NDFA is represented by digraphs called state diagram. The vertices represent the states. The arcs labeled with an input alphabet show the transitions. The initial state is denoted by an empty single incoming arc. The final state is indicated by double circles. Example, let a non-deterministic finite automata be Q is equal to A, B, C. Summation is equal to 0, 1. Q naught is equal to A. F is equal to C. Transition function del as shown below. Graphical representation. Acceptors, classifiers and transducers. Acceptor, that is recognizer, an automation that computes a Boolean function is called an acceptor. All the states of an acceptor is either accepting or rejecting the inputs given to it. Classifier. A classifier has more than 2 final states and it gives a single output when terminates. Transducer. An automation that produces outputs based on current input or previous state is called a transducer. Transducers can be of 2 types. Mealy machine, that is, the output depends only on the current state. Moore machine, the output depends both on current input as well as the current state. Algorithm for conversion from NFA to FA. In this video, we are going to see about algorithm for conversion from NFA to FA. Problem statement. Let x is equal to qx summation del x q naught fx be an NDFA which accepts the language L of x. We have to design an equivalent DFA y is equal to qy summation del y q naught fy such that L of y is equal to L of x. The following procedure converts the NDFA to its equivalent DFA. Algorithm. Input a NDFA. Output an equivalent DFA. Step 1. Create state table from the given NDFA. Step 2. Create a blank state table under possible input alphabets for the equivalent DFA. Step 3. Mark the start state of the DFA by Q0, that is, same as the NDFA. Step 4. Find out the combination of states, that is Q0, Q1 up to Qn for each possible input alphabets. Step 5. Each time we generate a new DFA state under the input alphabet columns, we have to apply step 4 again, otherwise go to step 6. Step 6. The states which contain any of the final states of the NDFA is the final states of the equivalent DFA. Example. The NDFA table is as follows. Let us consider the NDFA shown in the figure below. Using algorithm, we find its equivalent DFA. The state table of the DFA is shown in below. The state diagram of the DFA is as follows. Kleene's theorem part 1 and part 2. In this video, we are going to see about Kleene's theorem part 1 and part 2. Kleene's theorem, that is part 1. Theorem. For every alphabet summation, every regular language over summation can be accepted by a finite automaton. Proof. Every regular language over summation can be accepted by an NFA. The set of regular languages over summation is defined recursively, and we will prove the theorem by structural induction. The languages phi and sigma, where sigma belongs to summation, can be accepted by the two NFAs in figure respectively. Qi summation Qi Ai del I. We can assume by renaming states if necessary that Q1 and Q2 are disjoint. In the induction step, we must show that there are NFAs accepting the three languages L of M1 union L of M2, L of M1, L of M2 and L of M1 star. In each case, we will give an informal definition and a diagram showing the idea of the construction. For simplicity, each diagram shows the two NFAs M1 and M2 as having two accepting states, both distinct from the initial state. An NFA MU accepting the L of M1 union L of M2 is shown in figure. Its states are those of M1 and M2 and one additional state QU, that is the initial state. The transitions include all the ones in M1 and M2 as well as A transitions from QU to Q1 and Q2, the initial states of M1 and M2. Finally, the accepting states are simply the states in A1 union A2. If X element of L of M1, for example, MU can accept X by taking the A transition from QU to Q1 and then executing the moves, that would allow M1 to accept X. On the other hand, if X is any string accepted by MU, there is a path from QU to an element of A1 or A2. The first transition in the path must be a A transition which takes MU to Q1 or Q2. Because Q1 intersection Q2 is equal to 5, the remainder of the path causes X to be accepted either by M1 or by M2. An NFA MC accepting L of M1, L of M2 is shown in figure and new states need to be added to those of M1 and M2. The initial state is Q1 and the accepting states are the elements of A2. The transitions include all those of M1 and M2 and a new A transition from every element of A1 to Q2. If X is a string, X1, X2, where Xi is accepted by Mi for each I, then MC can process X by moving from Q1 to a state in A1 using A's and the symbols of X1, taking the A transition to Q2, and moving to a state in A2 using A's and symbols of X2. Finally, an NFA MK accepting L of M1 star is shown in figure. The transitions are those of M1, a transition from Qk to Q1 and a transition from every element of A1 to Qk. We can see by structural induction that every element of L of M1 star is accepted. The null string is because Qk is an accepting state. Now suppose that x element of L of M1 star is accepted and that y element of L of M1. When M star is in a state in A1, after processing X, it can take a transition to QK and another to Q star, process Y so as to end up in an element of A1 and finish up by returning to QK with a transition. Therefore, XY is accepted by M star. We can argue in the opposite direction by using mathematical induction on the number of times M star enters the state QK in the process of accepting a string. If M star visits QK only once in accepting X, then X is equal to A, which is an element of L of M1 star. If we assume that n greater than or equal to 1 and that every string accepted by M star that causes M star to enter QK n or fewer times is in L of M1 star, then consider a string X that causes M star to enter QK n plus 1 times and is accepted. Let x1 be the prefix of X that is accepted when M star enters QK the nth time, and let x2 be the remaining part of X. By the induction hypothesis, x1 belongs to L of M1 star. In processing x2, M star moves to Q1 on a transition and then from Q1 to an element of A1 using A transitions in addition to the symbols of x2. Therefore, x2 element of L of M1, and it follows that x element of L of M1 star. Kleene's theorem, that is part 2. In this, we prove that if L is accepted by a finite automaton, then L is regular. The proof will provide an algorithm for starting with an FA that accepts L and finding a regular expression that describes L. Theorem. For every finite automaton M is equal to Q, summation, Q naught, A, del, the language L of M is regular. Proof. For states P and Q, we introduce the notation that is L of P, Q for the language. L of P, Q is equal to X belongs to summation star, del star P, X is equal to Q. If we can show that for every P and Q in Q, L of P, Q is regular, then it will follow that L of M is because L of M is equal to union of L of Q naught, Q. Q belongs to A, and the union of a finite collection of regular languages is regular. Strings in L of P, Q cause M to move from P to Q in any manner whatsoever. One way to think about simpler ways of moving from P to Q is to think about the number of transitions involved. The problem with this approach is that there is no upper limit to this number, and so an obvious way to obtain a final regular expression. A similar approach that is more promising is to consider the distinct states through which M passes as it moves from P to Q. We can start by considering how M can go from P to Q without going through any states, and at each step add one more state to the set through which M is allowed to go. This procedure will terminate when we have enlarged the set to include all possible states. If X belongs to L of P, Q, we say X causes M to go from P to Q through a state R if there are none null strings X1 and X2 such that X is equal to X1, X2. Del star of P, X1 is equal to R and del star of R, X2 is equal to Q. In using a string of length 1 to go from P to Q, M does not go through any state. In using a string of length n greater than or equal to 2, it goes through a state n minus 1 times, but if n greater than 2, these states may not be distinct. For P, Q belongs to Q and J greater than or equal to 0, we let L of P, Q, J be the set of strings in L of P, Q that cause M to go from P to Q without going through any state numbered higher than J. The set L of P, Q, 0 is the set of strings that allow M to go from P to Q without going through any state at all. This includes the set of alphabet symbols sigma for which del of P, sigma is equal to Q, and in the case when P is equal to Q, it also includes a string A. In any case, L of P, Q, 0 is a finite set of strings and therefore regular. Suppose that for some number k greater than or equal to 0, L of P, Q, k is regular for every P and every Q in Q, and consider how a string can be in L of P, Q, k plus 1. The other strings in L of P, Q, k plus 1 are those that cause M to go from P to Q by going through state k plus 1 and no higher numbered states. A path of this type goes from P to k plus 1, it may return to k plus 1 one or more times, and it finishes by going from k plus 1 to Q. On each of these individual portions, the path starts or stops at state k plus 1, but don't go through any state numbered higher than k. Every string in L of P, Q, k plus 1 can be described in one of these two ways, and every string that has one of these two forms is in L of P, Q, k plus 1. The resulting formula is L of P, Q, k plus 1 is equal to L of P, Q, k union of L of P, k plus 1, k. L of k plus 1, k plus 1, k star. L of k plus 1, q, k. L of P, Q, 0 can be described by a regular expression for each k lesser than n. L of P, Q, k plus 1 is described by the formula above, and L of P, Q, n is equal to L of P, Q, because the condition that the path go through no state numbered higher than n is no restriction at all if there are no states numbered higher than n. As we observed at the beginning of the proof, the last step in obtaining a regular expression for L of M is to use the plus operation to combine the expressions for the languages L of Q naught comma Q, where Q belongs to A. Algorithm for minimization of finite automata. In this video, we are going to see about algorithm for minimization of finite automata. DFA minimization using Myhill-Nerode theorem. Input DFA, output minimized DFA. Algorithm. Step 1. Draw a table for all pairs of states, that is Qi, Qj, not necessarily connected directly, that is all are unmarked initially. Step 2. Consider every state pair, that is Qi, Qj, in the DFA where Qi belongs to F and Qj for vice versa and mark them. Here, F is the set of final states. Step 3. Repeat this step until we cannot mark any more states. If there is an unmarked pair, that is Qi, Qj, mark it if the pair, that is del into Q1, A, del into Qi, A, is marked for some input alphabet. Step 4. Combine all the unmarked pairs, that is Qi, Qj, and make them a single state in the reduced DFA. DFA minimization using Equivalence theorem. Two states are distinguishable if there is at least one string S, such that one of del of x, s and del of y, s is accepting and another is not accepting. Hence, a DFA is minimal if and only if all states are distinguishable. Algorithm. Step 1. All the states Q are divided into two partitions, final states and non-final states, and is denoted by P0. All the states in partitions are zeroth equivalent. Take a counter K and initialize it with 0. Step 2. Increment K by 1. For each partition in Pk, divide the states in Pk into two partitions if they are K distinguishable. Two states within this partition X and Y are K distinguishable if there is an input S, so that del of X, S and del of Y, S are K-1 distinguishable. Step 3. If Pk not equal to Pk-1, then repeat step 2, otherwise go to step 4. Step 4. Combine kth equivalent sets and make them the new states of the reduced DFA.